Section 5.7. Kind of more, basically it's a lot more practice with your U-substitutions. So, but let me remind you first, if we were to integrate 1 over x dx, what would I get?
ln absolute value of x.
Nice, ln of the absolute value of x plus your constant. So, okay. And likewise, if I had the integral of 1 over u du, it would be ln of the absolute value of u plus a constant. So our goal is to get something in this form, and then we can integrate it because we'll know the antiderivative. We'll start with problem number 8. The integral of x squared over 5 minus x cubed dx. Now this is not something for which we know the antiderivative of, at least directly. Nor can you integrate the numerator and divide by the integral of the denominator. There's no quotient rule for integrals. So we're going to be stuck making some kind of a substitution, or at least trying to make a substitution. Does anything suggest itself?
5 minus 3, or 5 minus x cubed.
Perfect. 5 minus x cubed. The nice thing about that is that when I differentiate a cubic polynomial, I get a squared polynomial. And you see that squared polynomial in the numerator. So I'll do it the long way once. Du by dx equals negative 3x squared. Multiply by dx and get negative 3x squared dx. Now for subsequent problems, I'm going to kind of skip that middle step. But you know, if you're running into trouble differentiating it, maybe you want to put it in. Let me rewrite this as x squared dx over 5 minus x cubed. And I've got x squared dx here. So I like to solve for that term in the integral. I get an x squared dx there, but I've also got that negative 3 out in front. What can I do with that negative 3? Yeah, move it to the other side, divide both sides by negative 3, or multiply by negative 1/3. And that's perfect. This is now exactly what I have in the numerator. And then in the denominator, what do I have? U. So negative 1/3 u, excuse me, negative 1/3 du over u. Perfect. I'll bring the 1/3 out in front. So negative 1/3, the integral of du over u. Negative 1/3 times the integral of, well, actually I can find the antiderivative of that now, right? So, a little Photoshop. Negative 1/3 times the ln of the absolute value of u plus a constant, or negative 1/3 ln of 5 minus x cubed. Yay, not so bad. So we're going to do a lot more like this to practice your U substitutions. Along the way, we'll also do some work with synthetic division. I'll give you a reminder about synthetic division, and then we'll do a few problems with synthetic division. But are we okay with this first one? Kurt, looking okay back there? All right, good. Let's try another one like that. Problem number 6. The integral of 9 over 5 minus 4x dx. So how about this one? What could I do with this one? Well, there's a couple things. You could bring the 9 out in front. That's just a constant. You have dx over 5 minus 4x. But then what? So, all right, so let's let u equal 5 minus 4x. And you know, I'll do it the long way one more time. What's the derivative of this with respect to x?
Negative 4.
-4. So du equals -4 dx. multiply both sides by the reciprocal of that. So negative 1/4 du equals dx. Yay. So we got a nice trade-off right here. We've got dx, and dx equals negative 1/4 du. So this becomes 9 times the integral of negative 1/4 du over u. You can, if you want, take an extra step and take this constant out in front. Negative 9/4 integral of du over u, which is negative 9/4 times the ln of the absolute value of u, plus your constant. Got to keep that constant around. So negative 9/4 times the ln of 5 minus 4x, plus your constant. Nice. Nice, nice. How are we looking on that one? Okay? All right. Before I do my next problem, I'm going to give you kind of a little bit of a reminder on synthetic division. So let's take, let's see, synthetic division. So synthetic division is for dividing by x minus a number or x plus a number. It has to be a binomial of that form. You can't have a coefficient in front of the x, nor can you have a squared term or any higher power. That's just that simple little linear term. But for that little linear term, it works great. So let's see that. Let's see an example of that. Let's take 3x cubed minus 4x squared plus 2x minus 7 and divide it by, say, x minus 5. Now, if you were stuck doing it the long way, now doing the long way is kind of a bummer. Doing the long way is like a 10-point problem on one of my beginning algebra classes. So it's not a fun problem. Don't copy this down. Here it is the long way. X minus 5 into 3x cubed minus 4x squared plus 2x minus 7. First, you'd have to figure out what do you multiply this by to get a 3x squared. You say, all right, 3x, I need to get a 3x cubed, so multiply by 3x squared. If I distribute that to both terms, I get 3x cubed minus 15x squared. But when you change the signs, this ends up as an addition. You get 11x squared. Bring down the 2x. Now what am I going to multiply by? Oh, well, plus 11x. So that's 11x squared minus 55x. Change the signs and add again, and I get 57x. And you can see that this is getting pretty nasty. Let me finish it up. The last thing I need to multiply by, that should be 1 5, not 2 5s. The last thing I need to multiply by is 55. No, 57. 57. So 57x minus 285. Ugh. And a remainder of 278. So a lot of work there to do it the long way. Let's take a look at what it is using synthetic division. Now with synthetic division, I'm going to first start by changing the sign of this number. So change the sign. So I'm going to put a 5 out in front. And then I want the coefficients. So the coefficients of my polynomial are going to be 3, -4, 2, and -7. Draw a line, but leave yourself some space because we need to write some more numbers here. Now, the first one, and only the first one, is going to get a 0. The rest of these, we're going to have some stuff that we can put here. And there's two basic things that are going to happen. You're going to add to go down and multiply to go up and to the right. So, starting here, I'll add going down. 3 and 0 gives me a 3. And then multiply. What do you think I should multiply the 3 by? 5 times 3 is 15. Now this process repeats itself. So add going down gives me an 11. Then what? 55. Multiply again. So 5 times 11 is 55. Add going down, 57. Now, next to the 57, actually between these last two terms, draw a little vertical line. The term that comes next is going to be your remainder. 5 times 57 is 285. Add going down, and you get 278. Okay, so what does all this mean? Well, you can see what it means by comparing it over here. This is going to be your constant term. That's going to be your term in x. That's the coefficient of x squared. And if there were more, it would kind of increase in order. So what this is telling me is that when I do this division here, the answer that I'll get is going to be 3x squared plus 11x plus 57 plus 278 over x minus 5. Yay. And that's what we needed to practice here. We're practicing that because it's going to become useful and it's some of the problems that we're going to face. So let's start with problem number 20, unless there's some concern about the method of synthetic division. Does this look familiar? Have a lot of you seen this before? Okay. Is it a good review, though? Okay. All right, that's good. So let's look at problem number 20, and we're going to call this 20-ish, because the way it's written in the problem in the book, you wouldn't be able to use synthetic division. It's the integral of x cubed minus 4x squared minus 4x plus 20. And in the book, they've got an x squared minus 5. If they had an x squared minus 5, you could not use synthetic division. You'd have to do something else. But I want to practice synthetic division on a meaningful problem. So here we go. Let's rewrite this by first dividing this out synthetically. So that's going to be a 5 out in front. And what are my coefficients here? 1, -4, -4, and 20. Between the last two of these, draw yourself a vertical line. And now work through that process of synthetic division. You don't have to write a 0 here underneath the 1. It's kind of understood to be there. 1. What comes up here next? 5, and then a 1. And then it's deja vu all over again, right? 5 and then a 1. Until we get to the last term, which gives me a 25. Can someone interpret these numbers for me? What does that mean? X squared plus x plus 1 plus 25 over x minus 5. That's going to make our integrand much more workable. Let's see that. So this integrand becomes the integral of x squared plus x plus 1 plus 25 over x minus 5 dx. Now the first three terms of this are things that you should be able to integrate just in your head. So rattle them off. What's the integral of x squared?
X cubed over 3.
Good. X cubed over 3 plus
X squared over 2.
plus
X.
x plus the integral of 25 over x minus 5 dx. So it's that last integral that we're a little bit stuck with. That's okay. What are we going to do to integrate that one? That's a good question. You know, I get this a lot. People want to split that up. Just kind of a nice note here. I can't split this up as 25 over x minus 25 over 5. It can't. You can bring the 25 out. Sure, 25 can come out in front. You're still going to be left with the integral of dx over x minus 5. Yeah. Yeah, perfect. Exactly. So a quick U-substitution. In fact, kind of a little heads up here for you. If I let u equal x minus 5, du by dx equals 1, and this is a really nice case of a U-substitution. Du equals dx. You can pretty much integrate this one in your head, all right, without necessarily doing a formal U-substitution. In fact, if you're comfortable with that, that's fine. Actually, we don't need to. I mean, you can take it out front or not. It's up to you. So what are we going to get? We're going to get x cubed over 3 plus x squared over 2 plus x plus the integral of 25 du over u, which is just 25 times the log of the absolute value of u. So x cubed over 3 plus x squared over 2 plus x plus 25 times the natural log of the absolute value of u plus a constant. Now this should look weird to you. What about this doesn't look right? You got u's and x's in the same thing, right? I want to finish this in x's, so let's just go back and substitute in x minus 5 here. So overall, x cubed over 3 plus x squared over 2 plus x plus 25 times ln of the absolute value of x minus 5 plus a constant. Yay. How are we looking on problem 20-ish? Okay. Now, rather than do another one with synthetic division, what I want to do is do some other problems that involve different tricks with your U substitutions. So one of the things that's going to be challenging for you moving forward is to figure out, well, what do I let U equal? And in this section in particular, there's, a few substitutions for U that you might not think of, at least right away. And I also want to practice some more of changing our limits of integration. It's going to start with problem number 22. So the integral of 1 over x ln of x cubed dx. All right, just doing a sound check. We still got sound. Good. I hate posting YouTube videos without any sound. Now, before you get going on this one and trying to figure out, well, what I'm going to let U equal, before we do that, are there any properties of logs that we can use that might make our life a little bit simpler? Yep. The 3 comes out in front using the power rule for logarithms. So the 3 can come out in front. In fact, let's take it all the way out in front of the integral, right? Might as well, it's a constant. So let's take it out front. 1/3 over dx x ln of x. And here's where there's a sneaky substitution here. It's not something that you're going to think of necessarily when you first see these integrals. I'll give you a chance though. Does anyone want to tell me what u is going to equal?
ln of x.
Yep, perfect. ln of x. Good job. So u equals the ln of x. What's interesting about this one is that part of your u substitution is going to be in the denominator. Usually that stuff's up in the numerator. But in this case, because of the nature of this substitution, du equals 1 over x dx, part of that term is in the denominator. That's okay. So, I don't know if it'll help you visualize it. Let me rewrite this a little bit as, say, 1 over ln of x times 1 over x dx. So I kind of mixed up the order in the denominator, but I did that to make sure that it was clear to see that this is your du term. All right. So what's that become then? This is 1/3 the integral of 1 over u du. What's the antiderivative there?
1 over the ln. Or ln.
Yeah, just ln. Yeah, just ln. So this is 1/3 the ln of the absolute value of u plus a constant. Now there's something a little bit ironic here in terms of the constant, or in terms of substituting in for u. What do I substitute in for u?
ln of x.
So I have the ln of x. That's okay. That's the way it worked out. That's it. There's a good follow-up problem to this one, but let me pause for a second and make sure you're on board with 22. Yeah. Here? Why? All I did was I took the dx off the numerator. I took the 1 over x out of the denominator and just kind of put them together here. Because that term is du. So these two are interchangeable. So I just kind of rewrote it a little bit. So that's my du, and this is u, so I have 1 over u. Anything else on this one? Appreciate the question. Let's try problem number 54. Now the thing about 54, it's very similar to problem number 22. It's a good follow-up in as much as we've got a definite integral. The integral from e to e squared of 1 over x ln of x dx. So, okay. What should we do for our u substitution? All right, let's set u equal ln of x. du is 1 over x dx as before. But then there's one more thing that I'm going to do here. One more thing that we should do. You don't have to do. But what's that one last thing we should do? Change the limits. Yeah, change the limits of integration. So I need to figure out u of e and u of e squared. So u of e is really just going to be the ln of e. What's the ln of e? Yep, ln of e is 1. What about the ln of e squared? Yeah, it's going to be 2. And let me show you kind of a rationale for that. The 2 comes out in front. I get 2 ln of e, which is 2 times 1, or just 2. The nice thing about changing your limits of integration is that we're not going to have to go back and work with the problem in x at all. We're going to finish it up using our limits. So Let's see what that's going to look like. So I'm going to have an integral. I'm going to split off the 1 over ln of x again, 1 over ln of x, and then I have a 1 over x dx. So I'm just bringing these terms together because that's going to be my du term. This is still from e to e squared. But when I change over to u, that's going to be the integral of 1 over u du from 1 to 2. And we're done with x's. We're done with e and e squared, etc. Just going to finish up the problem in terms of u's. Do I need a constant of integration when I'm working with a definite integral? No. So all I need is an antiderivative. I need ln of x. Now I could put the L on the absolute value of x. That's more accurate. But the values I'm going to plug in here are already positive. I'll get the ln of 2 minus the ln of 1. Does anyone know what the ln of 1 is? 0. Thank you. So that just disappears. Your answer here is the ln of 2. Now that's a nice exact answer. And sometimes I'll ask for an exact answer. And that's what I'd be looking for, is the ln of 2. Let's just practice calculating that on our calculators. Let's see how our calculators can do numerically. And I guarantee it's going to be a lot better than what you would get with Simpson's rule. So let's see. Hit the math key and then 9. Math 9. Do you know where to find e, the constant e on your calculator? It's right above the division key. So hit second and then divide to get an e. Come up here, second, divide, and then hit the squared key to get e squared. And then, let's see, we wanted 1 over ln of x, or 1 over x ln of x. Hit the second key and then the alpha key. 1 over x, and then the ln of x. Now what we should get is the numerical equivalent of this natural log of 2. And let's compare this to the ln of 2. I have a feeling that they're going to look remarkably similar, and they do. All right. How are we looking on that one? Okay? You okay with 54? Does anyone need any help finding that on your calculators? Get it? Which one? Oh, math and then 9. Now, if you have a function that responds, or if you have a calculator that responds with fn int, then it'd be fn int. You'd have to type the function 1 divided by parentheses x ln of x, comma x for your variable, comma lower limit, in this case e, and then the upper limit e squared. So that's what it will look like if you don't have an operating system that's up to date. Anything else? Okay. So I think it's time to build a houseboat. So you can take kind of a rest for a second. To build a houseboat, what we're going to do is integrate 1 over cabin d cabin. There we go. So 1 over cabin d cabin. Well, we've done enough U-substitutions, you can kind of see what's coming. We get the ln of this. But there's an important thing we got to remember. That constant, right? So you've got a log cabin plus the c. So log cabin plus the c is a houseboat. Yay! All right, some of you noticed that it's on an old exam. So that's probably why you're not rolling in the aisles with laughter at this point. All right. Anyways, a brief little cheap aside. Yeah, I know. I'll keep my day job. Okay. Let's take a look at problem number 72. You know, I think I might do problem 72 this way. Let's just do a sound check. Got sound? Yes, still have sound. Let me know if we run into some more videos without sound. So, problem 72, boy, it just doesn't show up good on this. I want to find the area underneath the curve.
The book is covering the light.
Yeah. Let's see here. Yeah, there you go. Perfect. Yeah, not much I can... that's not too bad. There we go. So we want to find the area underneath the curve of sine of x over 1 plus cosine of x between pi over 4 and 3 pi over 4. But let me kind of look at it here real quick. So not as nice of a graph, but at least we can see what's going on a little bit better. Here's your function, sine of x plus 1 over cosine of x. We want to find the area underneath this curve between 2 points, pi over 4 and 3 pi over 4. So let's do that. Get back over here. Now go from pi over 4 to 3 pi over 4 sine of x over 1 plus cosine of x dx. Suggestions on how to deal with this one? I'm open. This is not a basic form. It's not like integrating, x squared or something like that, for which we know an antiderivative. We need to do a little something to jumpstart this problem. What would that be? I've gotten that suggestion a couple times. Let me be very clear about something. If you have a over b plus c, you can't split that up into a over b plus a over c. It doesn't work that way. If it was the other way around, if you had b plus c over a, then you could split it up. You could do b over a plus c over a. That one works. This one will give your instructor a headache when I grade your paper. All right, can't do that second one, or that first one. Other suggestions?
Split up the top and the bottom. I would assume that you'd have to rewrite 1 plus cosine x.
If this was a cosine squared, you might be able to start thinking about a Pythagorean theorem, but it's not a squared there. So it's a good thought, but Kurt, think you had an idea? Let's try that. Let's let u equal 1 plus cosine of x. What's du? What's du going to be in this case? Well, let's do du by dx is minus sine of x. Du equals minus sine of x dx. Dylan, was this your suggestion?
Yeah, I was just thinking that, but I didn't think it was that simple.
Oh, okay. I promise not to put simple problems on your exam, okay? Everyone will be able to thank you. All right. I've got a sine of x dx here already. What's one thing I need to take care of, though? The negative. So let's kick that over to the other side, divide both sides by -1. What else should I do in this one? Perfect. You're my champion today. Change the limits of integration. So I need u of pi over 4, which is going to be 1 plus cosine of pi over 4. Oh, see, you all thought you were done with your trig, didn't you? It's like, oh, cosine of pi over 4. I can see digging deep into the brain. Cosine of pi over 4. Anyone? Square root of 2 over 2. And likewise, u of 3 pi over 4, 1 plus cosine of 3 pi over 4. Now on the left side of the line, pi over 2, cosine is going to be negative. So this is going to be 1 minus square root of 2 over 2. So nice. I think we've got all our ingredients to change our integral. So the limits now are going to be between 1 minus root 2 over 2 and 1 plus root 2 over 2. Sine of x dx can get replaced with minus du. So it's going to be minus du over what? U. Over u. Well, that's not too bad. We can take the negative out in front if you want. Doesn't matter. Negative 1 minus root 2 over 2. 1 plus root 2 over 2. 1 over u du. And that's just going to integrate as the log. Let me remind you of one other trick, though. And it's just, I'm only reminding you of this because we got that negative sign out there that's mildly inconvenient or mildly a nuisance. If I change the order of the limits of integration, what happens with that negative sign? Yeah, it's going to disappear. All right, so if I integrate from 1 plus square root of 2 over 2 to 1 minus square root of 2 over 2 of 1 over u du, then it flips the sign there. So that's a good trick. You know, then I'm not going to make a silly mistake with my integration or forgetting to distribute a negative sign. This is now the ln of the absolute value of u between those two limits, 1 plus root 2 over 2, 1 minus root 2 over 2, which is the ln of 1 minus root 2 over 2 minus the ln of 1 plus root 2 over 2. Now I'm not going to really ask you to go crazy far with this. This is a nice exact expression. You can rewrite this using the quotient rule for logs as 1 minus root 2 over 2 over 1 plus root 2 over 2. And that can actually be further rewritten as the ln of 2 minus the square root of 2 over 2 plus the square root of 2. I'd probably be okay with it here. I'm not going to try and turn this into an algebra class. But here's a nice closed form expression, and you can calculate the answer from there if you wanted to. You can also compare it to the area of that curve that you get off your calculator. So let's just take a quick look at what that would be. ln of 2 minus the square root of 2 over 2 plus the square root of 2 something's wrong here. Did I put these in the wrong order?
The pi over 4 and the 3 pi over 4 should be flipped.
Or it should be 11 plus square root 2 or 2 minus the other one.
Yeah, the order is wrong. Well, what's clearly wrong about this?
The answer is negative.
The answer is negative. If you look at the function, if you look back at the function, this area lies above the x-axis. So clearly something's wrong. I missed a sign someplace, despite my objective or my intentions not to. So let's go back and see where I missed that sign. Oh, yeah, I mixed them up down here. These were put in the wrong order. Yeah, I should have had the plus here and the minus here. Okay. All right. No, these were backwards when I substituted them because of the negative. So, yeah, I substituted them backwards. So that's why the answer is really opposite of what it should be. These would be flipped. Okay, I'm not going to try and go through and sort all that out. I just put in these limits in the wrong direction. So the true answer is really opposite of that, which should be 1.7627. Let's do a couple more here. All right. I know I muffed this one a little bit, but are we still okay with the general amount of work we did here? Is there a specific question on this one still?
When would you know how to change that 3 pi over 4 and pi over 4 to like real numbers without using?
You mean these?
Yeah, because while you was doing it, I was just.
You're just leaving it as cosine of 3 pi over 4?
Yeah.
I would want that done. So I guess the answer is always would be the answer. Always change cosine of 3 pi over 4 to this, or cosine of
Whatever that is, the S. You know how you.
the integral.
Yeah, you know how you have. Okay. You know how at first you have 3 pi over 4 and then pi over 4?
Oh, you mean up here? Change the limits of integration?
Yeah.
You don't have to. If you don't change your limits of integration, then really what you should be doing is, in this next step, you'd write from A to B. Because the limits of integration of pi over 4 to 3 pi over 4 only refer to the variable x. They don't refer to the variable u. So you'd write A to B, and then once you found the antiderivative, you'd replace A and B with your original limits, pi over 4 and 3 pi over 4, and then go back to the expression 1 plus cosine of x. So that would be the way to do it. You'd end up with the same thing. It's just a different way to do it. I like changing limits and being done with them as opposed to going back to units of x. Dylan?
Just have an alt break where I get 2 minus square root of 2 and then.
From this to this step? Okay. That's a good question. So what you have here in the absolute value is what's called a complex fraction. And so what I'll do to simplify that is I'm going to multiply both the numerator and denominator by this term, by 2. So if I distribute the 2, 2 times 1 is 2. 2 times this cancels that out. So that's where I get this. And then likewise in the numerator. So yeah, it's something I didn't show, but I appreciate the question. Okay, I think we're done with that one. So let's take a look at problem 52. Maybe you should do problem 52. Just double check yourself on something. The integral from -1 to 1 of 1 over 2x plus 3 dx.